So, okay, I'm not going to show you any cool technologies, but I'm going to set a challenge. And I regard it as the biggest challenge of all. It's, it's the save the planet type challenge. So let me, before I start telling you about that, tell you a little bit about myself. So I picked a title for the talk. Actually, the title of the talk was Systems, Complexity and Global Change. And then I added this Surviving the Anthropocene as my tagline. Are people familiar with that term, the Anthropocene? Yeah? One person's heard it. Okay. All right. So I'm going to have to spend some time explaining that. But before I do, let me just give you a little bit of background on me. So I'm a professor in computer science. If you want to get hold of me, that's my blog. So you can go and read the kind of stuff I do. There's also somewhere an official university page telling you the research and teaching that I do. The blog's more interesting. Except I don't get time to update it these days. Okay, so let me just jump in and tell you about the research that I do. And this is how I characterize it. What I do is what I call climate informatics. And the best definition I ever came up with that, well, it's the intersection of three fields: climate science, computer science, and information science. And for ages, I didn't have the information science there. I said, it's the intersection of computer science, which is what my background is, and climate science, which is what I got interested in as an area of application. And of course, in that whole intersection, you get all sorts of things. You get the people building computer architectures for supercomputers to run simulations on. You get the folks trying to build exascale computing. And I don't do any of that. So I needed a way to say, look, that's not what I do. And then by adding the information science in, I said, look, I'm really interested in the question of, let's see if this works. No, actually, it's the next one. I'm interested in the question of how do we get wisdom about the future from the data and models that we have available at the moment. By the way, if people haven't seen this graph, this is from a fabulous paper by Russ Ackoff, who's one of the key leaders of systems thinking. The paper is From Data to Wisdom. And his argument is, we talk a lot about knowledge, and the course is about knowledge, right? You guys are building knowledge media. And he says, well, yes, but knowledge, data, information, and knowledge, however you define them, are largely talking about the past. They're talking about stuff we found out about the world. If we face forward to the future and we want to make wise decisions, we have to go one step further. And he talks about essentially two different dimensions here: the seeing how things connect and your level of understanding about the world. And as you move outwards on both of those dimensions, you get to wisdom, however we define it. Was there a question? By the way, feel free to interrupt me. It's much more fun if you guys throw me off course and we talk about what kinds of stuff you'd like to know. So that characterizes what I do, which means when I deal with climate science and climate scientists, I'm interested in what they do and how they do it. I'm interested in the data that they work with, the simulation models they work with. But I'm really interested also in how that information gets communicated with other audiences. So I'm interested in how scientists engage, for example, with the blogosphere, or fail to engage with the blogosphere is quite often. So I'm interested in why, what is it that stops scientists getting out and talking more generally about what they do? Which just brings me back to the one I skipped over there. A lot of the research that I've done in the last few years is focused on this question of these models that the scientists use, these simulation models. What are they? How do they build them? And how much should we believe the output of these models? And I'm probably guessing people have never really looked at climate modeling and what climate scientists build. So maybe I should do a quick 5-minute what is a climate model? Okay. Oh, hang on, I've got to go. I don't think I had this set up. So we have to look inside the black box. There we go. It works. Okay. All right. So my simplest definition of a climate model is it's solving the equations of fluid dynamics on a rotating sphere. So you take the globe, you divide the atmosphere and the oceans up into a number of cubes, and because you're going to do numerical simulations over every cube at every time step in the model, your cubes have to be pretty big because your computer can't run them that fast. So we're typically talking cubes where you can see on here roughly how big they are typically in a, let's say a climate model from the last decade, talking 10 or 100 kilometer, actually no, these are more than 100 kilometer cubes. But anyway, the more computer power you give the scientists, the smaller they make the resolution of the grid. Okay, because there are lots of phenomena that they're interested in, so small-scale weather phenomena, that only appear on a high-resolution grid. In fact, what happens is as you increase the resolution of the grid in your model, certain phenomena spontaneously appear. They haven't been programmed into the model. One of the obvious ones is hurricanes. With a coarse grid, you don't get hurricanes forming in your model. At some point, the resolution of the model flips and suddenly they start forming in the model. And they're not programmed in, what you program in the model is the equations of motion. So where the wind is, where heat is moving, where mass is being transported. You've got the rotation of the Earth. You've got the magnetic field of the Earth, the gravitational effect of the Earth. You've programmed all the numerics in for that, and then you just let things happen.
Sorry, yeah. So you're saying that simply by increasing the resolution, the computer, without knowing what a hurricane is,
exactly,
the evidence of them begins to appear within the model.
Yes,
that's creepy.
It's weird, but what it means is there's a bunch of equations that basically capture all of the motions in the atmosphere and ocean.
So does that?
And if you get those right, the right phenomena appear in your model.
So does that tell us? Like, do you take from that saying that a hurricane is something that is more affected by that, because you're taking the highest level. If the resolution is small, you're taking only the highest level dynamics.
Yeah.
And with only that information, you're able to zero in and start to see smaller phenomena.
So the way a hurricane works is it's a combination of sea surface temperatures. You actually need warm seas to give it energy. And it's to do with the convection off the surface of the ocean. It's to do with the spin of the Earth. You know hurricanes always spin in the same direction in the northern hemisphere. And a few other things to do with the interaction of the ocean and the atmosphere. And if you get all those right, and your model is high enough resolution, hurricanes will form. The storms will start in the model, and the storms will start spinning, and they move. Now, what you don't get, of course, is any particular hurricane, any real hurricane. So you can't know where hurricanes go. You can't always figure out that a certain number of hurricanes will form this season and they'll head off in the following directions. But you get things that behave like real hurricanes. Okay, so it's not a weather prediction tool, but it is a simulation of the real phenomena of the climate system. Make sense?
So it seems like if you put in what happens rationally, like a yes or no, like you would with a computer program, like 1 or 0.
Right.
Eventually, if you refine it enough, you'll get something like hurricanes, right? That's kind of what you're saying, is that hurricanes are a rational kind of occurrence in the weather system.
It's essentially, if you understand chaos theory, it's basically a chaotic behavior, okay? And if you get enough of the mathematics of the chaotic processes in the atmosphere, some of the natural phenomena that you will expect will emerge.
Has anything, I mean, I don't know how pinpoint this type of stuff is, but is there any sort of like weird weather phenomena that meteorologists, like water spouts, or has any of that stuff popped up or anything? I don't
know about water spouts. Water spouts would be too fine a resolution.
Yeah.
Because remember, these grid cells are still pretty big, so you need large scale. A hurricane's pretty big, so it'll pop up even with a reasonably coarse grid. Things that come down to meters or tens of meters aren't going to show up in the model.
I guess that was a bad example.
Okay, but I have to say things show up in the model that aren't in the real world as well.
That's
okay. And for example, one of the things that often shows up in these models is what they call a grid point storm. So you get a storm that occurs at exactly one grid point and nowhere else around it. And what's happened is because of the approximations in the model as numbers are being passed around between these grid cells, suddenly all the energy got sent to one point, and the only thing the model knew how to do with it was there had to be a storm at that point. And that's not a real phenomenon. Okay, storms affect a reasonable area and they move around. So there's suddenly something going on in the numerics of the model at this one grid point that's just wrong. So you get things that occur in the model that don't occur in the real world. And so these models have evolved over a period of 30 or so years. In fact, the very first models were built in the 1950s to run on the very first computers. And it's very much tied up with weather forecasting as well, because a lot of the numerics in the weather forecast models is the same as what's in the climate models. So the two have grown in parallel with each other, and they've grown in parallel with the growth of supercomputers. So, if you look back over the last 50 years to say who consistently uses the fastest supercomputers in the world, climate scientists are there along with atomic physicists and a few other people, but they are one of the major consumers of supercomputing facilities. And what they do is they just add more and more detail to the model. Every year they say, oh, there's something else we could get into this model, and they continue adding more of the theory about how oceans and atmospheres work, and then getting the model more and more accurate.
How many orders of magnitude are they from model and simulation?
How many? Say that again.
So how, approximately over the 50 years?
Yes.
From what the resolution started at to what it is now, would you say how many times has it doubled?
I have no idea. I could probably sit and work it out, but it's got to be in the billions.
Yeah.
I mean, there are simulations now of the very first programs written in the 1950s that run on a cell phone. Back then, they needed a room-sized machine to run on. And there was because you got the time dimension as well. So the very, very first ever weather forecast was run in 1949 on ENIAC, which was one of the very first machines. It took 24 hours to compute a 24-hour weather forecast just for North America, using a grid that only had something of the order of 30 grid squares spread out over North America. Okay, so it took 24 hours to run. So at the end of 24 hours, it knows what the weather is now. But they were vastly excited by this because they said, oh, well, that's great. If we compute it kind of keeping up with the real weather, all we need is a faster machine, and now we've got real weather forecasting. And of course, you wait a few years and you've got a faster machine. Now you can run that in less than a second on any old cell phone. And I don't know if that gives you a sense of what the... probably doesn't, right? But
well, existential crisis.
All right, so the other thing is you can do, you can calculate it from Moore's law. Are people familiar with Moore's law?
Yes, that's what I was referring to.
Right, so Moore's law has been pretty consistent, at least over the last 30 years. There's a little bit of noise in the data before that. We double our processing power at roughly every 18 months. So calculate how many doublings there are in 30 years.
Well, isn't that the point? Is that we're not that many doublings away from a 1-1?
With the real physical climate system, no.
No.
I mean, so here's the real problem. The biggest issue with climate models is simulating clouds. Mm-hmm. So clouds have a massive role to play in climate. Okay, they block incoming sunlight. They're also water vapors are greenhouse gas, so they trap outgoing radiation. They're white, so they reflect the sunlight. And so there's a number of different roles that clouds play. To simulate a cloud, you have to get down to the microphysics. You almost have to get down to the level of the molecules in the cloud, and how, when you get dust in the air, how water molecules attach to the dust and form droplets, and how clouds are formed. It's crazy. That's not coming anytime soon, at least not on a global scale. So there are cloud simulation models, so they'll simulate like one cloud. All right, and you wait several weeks for a result.
So you have all these cubes, and each cube has an algorithm of all the things that are necessary, like gravity, the wind, blah, blah, blah.
Yeah.
And then that constantly changed, like constantly updated itself as the world moved. Then you would essentially see a hurricane move from cube to cube.
Exactly. Yes.
Okay.
Yes. And so you'll typically run it on something like a 3-hour time step. So every 3 hours, for every cube, you recompute what's going on now. And at the interface of every cube, you're looking at the transfer of heat and mass and energy.
You're seeing seasons move by.
Yes, exactly. Exactly. So you run it on a 3-hour time step for every grid cell on the thing. And then, of course, if you're interested in climate, you want to run it, let's say, for 100 years to simulate climate change. So on the fastest supercomputers today, at the resolution they're running, you'll typically wait a month for your run to complete. So the scientists are used to this. They'll load up an experiment, leave it running, wait a month, come back, and then they've now got a complete simulation of a century's worth of climate for the whole globe. If you wanted it quicker, you can reduce the resolution, but then some of the small-scale phenomena disappear. Why was I showing you this? Oh yeah, so one of the problems with, I don't know how much you want to get into this. I wasn't going to go there, but one of the problems with the traditional grid is you get convergence of the grid cell at the poles. So your grid cells get smaller and smaller as you go towards the poles, which is a real problem for computing what's going on. The smaller your grid cell, the smaller a time step you need to take account of the movement of stuff within that cell. And so they play all sorts of tricks. So the oceanographers, for example, rotate the grid so that the poles are over the land masses. And then they don't have to have that singularity point in the ocean simulation. The atmospheric scientists can't do that, so they play other tricks. They're working with different kinds of grids. So this one here is the cube sphere. So imagine the globe inside a sphere, and then you project the sphere back down onto the globe, so you get the 8 corners. So you still get a little bit of noise going on here where you've got each of the corners, but it's a lot less than you would with the 2 singularities of the 2 poles. Okay, so it's better, but it's a more complex grid. Where they're really going is these kind of geodesic tiling grids. And this is where the latest research is, variable grids, because what you really want is you want fine resolution where interesting things happen and coarse resolution everywhere else. So for example, along the coastline of South America where the ocean winds interact with the Andes, you want really high resolution grids because there's all sorts of phenomena along that coast that aren't captured in current models because if you imagine how much the land rises as you go up the Andes in one grid cell, it happens just too quickly and the model can't capture what happens as those winds climb up the sides of mountains. So this is really complex to program. What else was I going to show you? So so this is kind of where we are now. We're simulating the coarse motion of the atmospheres. So the Earth basically acts as a heat engine. It pumps heat from the equator, which receives the most sunlight, towards the poles. So there's this continual transfer of heat from the equator, both north and south towards the poles, and it does it through these cells of air, and it's to do with the interaction between sunlight, energy coming from the sun, and the rotation of the Earth, and there's this coarse scale phenomenon in the atmosphere. So we can simulate all of that, and most of the science now is around what happens if you couple that with simulation models of other things like the land surface, the carbon cycle, the growth of plants, the production of the soil, trapping of carbon in the soils, release of carbon as the soils decompose, movements of land ice, and the way that sea ice grows in the winter and shrinks in the summer. And so you want that all coupled in with your simulation model. So that was my quick tour of climate. Right, so I want to step back from climate change though and characterize climate change as one problem. It's a big and it's an important problem, but it's one symptom of a much larger system that we need to think about how it works. And that's where I get to this idea of the Anthropocene. So let's see how we go. Okay. And it's largely to do with the story of the growth of civilization and the growth of the human population, specifically over the 20th century. So this graph here shows you world population, that's the blue line, versus carbon dioxide emissions, that's the red line. And what you can see is basically two exponential curves. And they're exponential curves because they are processes that feed on themselves. So the human population grows, and as it grows, we get wealthier. And as we get wealthier, people are more able to survive to adulthood. The more people that survive to adulthood, the more babies they have, and the cycle just accelerates. So you've got this exponential growth in population. So it's driven partly by the fact that as a population gets successful and solves problems, it's able to support more people. But it's also driven by one other major factor here that's new in the history of human civilization, and that's the discovery of cheap energy. So in the 1800s, we discovered oil and coal, and we discovered how to extract them very cheaply. In the history of human civilization, this is the cheapest energy we've ever had, maybe apart from slave labor, which was essentially free, but we've abolished slavery, right? This is the cheapest form of energy we've ever had. And it's driven the technological change we've seen, it's driven the growth in population, it's driven the growth in food production, for example, to feed all those people. And then the question is, well, no exponential growth curve can go on forever. It's just physically impossible. If you're living on a planet, on a finite-sized planet, it's impossible for this curve to keep growing exponentially forever. So then the question becomes, well, what point does it stop growing? And what happens then? And we've all lived in this era where growth is seen as a good thing. Growth is healthy, growth is what we go for. If you read the newspapers, you look at the state of the economy, everybody talks about growth. If we're in a position, let's say a recession, when the economy stops growing, the politicians all run around and say, how can we get back to growth? So we've all been raised in an era where growth is considered a good thing. At some point, it has to stop. So, for example, 1/3 of the Earth's land surface at the moment is currently given over to food production. Okay, there's not much more space to grow food production. There are a few more remaining forests we could chop down, but there really is not much room for expansion of that. But if we're already using 1/3 of the land surface area for food, and this population keeps on growing, what happens? The answer is, well, we can't feed people. So this isn't the only pair of exponential curves. Almost any indicator you look at has been exponential over this period. And I'll point you to a brilliant paper in, I don't even know the title of that journal, Philosophical Transactions of Mathematical Physics, Science, Engineering. It's got everything in the title. Anyway, so the paper is called The Anthropocene, Conceptual and Historical Perspectives. And the paper sets out this concept that humans are now the dominant driver of change on the planet. And if you look back in kind of geological history, geologists divide the history of the planet up into these major eras, each one dominated by different kinds of physical processes going on to do with the kinds of rocks that were being formed, to do with the kind of animals and plants that were able to live on the planet in that particular era. So we currently live in the Holocene from a geologist's point of view. Well, these people and a few others put forward this argument that says actually human impact on the planet is now so visible in so many areas that you could argue we've now entered a new era. And they call it the Anthropocene, anthropo from human influence. And it says all of the old drivers of change have now been superseded by human activity, and we're pushing the planet in directions it's never been before. Not physically pushing it, but pushing the planetary systems in directions they've never been pushed before. And so they set out these graphs to hammer home the point. So here's a whole set of exponential curves, right? So there's population, there's total real GDP, foreign direct investment, damming of rivers, water use, fertilizer consumption, urban population, paper consumption, McDonald's restaurants, motor vehicles, telephones, international tourism, every single one of them climbing up this exponential curve. And it goes on. There's a whole set more. All right. Carbon dioxide concentrations in the atmosphere, nitrous oxide in the atmosphere, methane in the atmosphere, ozone depletion, surface temperature of the northern hemisphere, great floods, ocean ecosystems. They mean actually percentage of fisheries fully exploited. We're getting up to 100%. Shrimp farm production, nitrogen flux. So this is just the amount that we're pushing nitrogen around in coastal zones. The coastal zones are just swamped with nitrogen fertilizer, which is disastrous for the ecology of coastal oceans. Loss of tropical rainforest and woodland. Amount of domesticated land. That's that figure I said now is at about 30%. Number of species extinctions. We're currently living through the 6th great extinction event of the Earth. And if you know your geological history, you know a few of them in the past. One of them was caused by a meteor impact. That was the end of the dinosaurs. Several others were caused by biological processes that went out of control and messed up the composition of the atmosphere. So we're currently in the middle of the 6th one. Species are going extinct faster than they have, at least in human history. And so if you put all that together, and you say, well, what's the driver of this? The driver really you can boil it down to 3 dimensions. One is this exponential growth in population. I don't know if can you guys see the numbers at the back here? So this is the figure for the turn of the 20th century. So the turn of the 20th century, 1900, 1950, and now. Actually, this was last year. Right? We've grown a little bit even since then. But what you can see is an exponential growth in population, an exponential growth in affluence, the amount here measured in GDP. So the amount that money is flowing around and allows us to do things, so economic activity, essentially. And an exponential growth in the amount of technology we have available to us. Here just measured in terms of patent applications. Okay, and then the argument is, right, multiply those 3 together, and the volume of that space is some sense of the growth of human impact on the planet. Okay, because we're extracting resources to build that technology. The more money we have, the faster we can do that. So we're mining the planet faster than we ever have before. We're digging up all these natural resources. We're building this technology. We're typically then throwing it away after a couple of years. We've got waste flows larger than we've ever had before. There's some interesting work that views human society in terms of its metabolic rate. You view human society as a metabolism. It takes in resources, it produces wastes, and it processes those things at a certain rate. Okay? And then the question is, what are the limits? What are the limits that we get to where we can no longer keep consuming resources faster and faster and producing wastes faster and faster? And, we can do a certain amount of recycling so that instead of consuming raw resources and producing wastes, there is some reprocessing of materials within the system. But all the time we're using energy to do that, and the vast majority of our energy comes from fossil fuels, and so we've still got the pollution problem from those, which is changing the composition of the gases in the atmosphere. And we're a long way from being able to solve that problem, let alone all the other problems of resource consumption and so on. So that leads to an observation that we are facing massive challenges all at once in a large number of different spheres. And they're all interconnected. So this comes, by the way, from a great presentation from Sir David King at the University of Oxford, who was the UK's government science advisor. He stepped down a couple of years ago. For many years he was their main science advisor. And he points out, look, okay, in all of these systems, we are facing increasingly a crisis in dealing with the rates of change. And if any one of them is hard to solve but could be done, But solving all of them together is a huge problem because they all interact. So let me think how some of these interact. Food production. For example, we solved a food crisis in the 1970s through the Green Revolution. Okay, we massively expanded. So in the 1970s, 1960s and 70s, there was a lot of discussion the world was going to run out of food. Because looking at food production levels then and population growth, it was quite clear a crisis was on the way. There was this massive revolution in food production that was largely driven by pouring a huge amount more energy into the system. So we went for these massive mechanized farming processes that basically ran on oil. So we poured a huge amount of oil into our farming practices to ramp up food production. So we solved the food crisis in the 1970s through the Green Revolution. But we solved it by increasing the energy demands. So that means we solved this problem essentially by making climate change a whole lot worse and by getting to the point where we're starting to run out of oil, or we're starting to run out of cheap oil. Yeah.
And then the oil fertilizers actually poison the soil.
Right, and then okay, so
we're even more screwed.
Yes, so the fertilizers we're pouring into the soils run off the land, pollute the waterways, pollute coastal waters, and that affects our water resources. Oh, we're also, of course, sucking out water out of the world's aquifers far faster than they're being replenished. So we're heading to a crisis on usable water supplies. And at the same time, of course, climate change is melting the mountain glaciers, which feed a large amount of the world's freshwater supply. Cut off all that supply, and you've suddenly got a lot less water flowing through the rivers anyway. So we've got complex interactions in all of these different spheres. So this idea then of the Anthropocene has kind of taken hold. There was a recent issue of The Economist, when I say recent, this was a year ago, just over a year ago, with the Welcome to the Anthropocene as its cover. And it's setting out this interconnected set of problems largely due to the number of humans on the planet and their economic activity. And plenty of discussions then about how to understand the drivers of these changes, understand their impacts, and figure out how collectively people can start to unpick the drivers or separate the drivers from their impacts. So there's a lot of talk about collective action. There's a lot of talk about how, not so much what individuals can do, but what communities can do, what cities can do, where a very large number of people working together need to solve some of these problems. One of the hard things to get your head around here is, well, how much should we worry about each of these different systems? Where are the limits? Can we predict a particular kind of crisis kicking in because we've overstepped some limit somewhere? So we need the right set of mental tools to think about this, to think about these global systems as a whole, to think about how they work, and to think about limits as they exist and how close we are to the limits. So the best piece of work that I found on this is some work from the Stockholm Resilience Centre, which is a major interdisciplinary research centre in Stockholm. And they did a huge big study about 18 months ago, and it was published simultaneously in where was it published? I've got the reference coming up in a moment. Let me tell you about that. So the concept was to identify a number of key indicators, a number of key variables that tell us about what's going on the planet as a result of human activity. And for each of them, to identify the threshold whereby we tip that system into some new regime. Okay, so if you're down here, the control variable you're worrying about can vary quite happily within some space, and it's safe. It doesn't have a dramatic impact on human activity. And then there's some zone where it's really hard to predict, but the closer and closer you push it, you're pushing it to some threshold where you tip over. For example, use of oil. At some point, because we've extracted all of the cheap oil, and the stuff that's left gets more and more expensive, the price of oil goes up. At what point does the price of oil rising suddenly cause a disaster in the economy? And we know at some point it must, because oil can't continue to rise forever and us run the economy the way we're running it right now. Okay, at some point something breaks down. So where is that? What's the price of oil where this starts to break down? Or for climate change, we're putting out these greenhouse gases into the atmosphere. At what point do we reach a threshold where we suddenly tip the climate system into some new regime? And maybe we start some runaway feedback process that once it's started can't be stopped. So that's the conceptual tool for thinking about it. We want to identify what these variables that matter are, what this zone of uncertainty is, and if we can put a threshold value on it, where's the boundary of the safe space? And they did this there's the reference up the top there, but you can't read it. Hang on a sec. Let me tell you what the reference is if you need it. It's in Nature, it's older than I thought, September 2009. The title of the paper is A Safe Operating Space for Humanity. And they identified a number of these systems where they could pick out a variable and they could identify a threshold and then calculate how close we are to the threshold. And so this is their set of systems. They looked at climate change, ocean acidification, ozone depletion in the stratosphere, the nitrogen cycle and the phosphorus cycle, global freshwater use, change in land use, biodiversity loss, atmospheric aerosol loading, that's the kind of particulate pollution, and chemical pollution. Those two they weren't able to quantify, so they said we don't know where we are on those two, but those are the things that we have to calculate. The green circle represents the safe threshold for each of these systems. So if we're within the green circle, we're still operating within that safe zone. If we've gone outside the green circle, we've potentially already tipped this system into a crisis. And they said there's 3 of these that we've already gone way outside where we should be. Biodiversity loss, which is the worst, the nitrogen cycle, so the amount of nitrogen flowing where it shouldn't be flowing, and climate change. And there's a couple where we're getting close, so the phosphorus cycle and ocean acidification, we're getting close. Now the problem with this paper is that it's a first attempt to do this. So you can look at any of the thresholds they identify and you can say, you know what, that's a completely arbitrary decision point that you've made. And there is some discussion going on in the literature now of this to say, well, where are the real thresholds? These guys made a first cut at it. They might be out. They might be out by an order of magnitude. They might be out by more than an order of magnitude. So we need some discussion around where these boundaries lie. So where do I want to go there? So let me talk a little bit more about climate change specifically and why the argument is put forward by these people and by many others that we've already passed the threshold. How long have I got, by the way? When do you want me to stop talking? Well, we should move into a more interactive discussion at some point. Right, let me just take you back to some basic ideas around climate change. How many folks feel they have a good understanding of how climate change works, what the basic physics is? We were all taught it in high school, right? Or something. Maybe not. All right, so going back to those models I showed you earlier, the scientists that use them are basically, there's a huge number of experiments they'll run on these models just to improve their understanding of how these systems work, to check that the theory corresponds to reality. But largely, the key questions, and these are the questions that are already now well understood, boil down to how do changing concentrations of these gases in the atmosphere lead to temperature changes of the global temperature of the Earth. And this is typically known as climate sensitivity. And it's typically phrased as, for each doubling of carbon dioxide in the atmosphere, measured in parts per million, what's the corresponding temperature change measured in degrees centigrade? And that question was framed in that way about 30 years ago, and there's been study after study after study after study in that period, all of which has failed to narrow down the uncertainty range. Okay, the uncertainty range is usually quoted as something like about 1.5 to 3, if I remember the numbers, 1.5 to about 3.5 degrees centigrade. That's a big range. Okay, that's the temperature rise per doubling of the concentration of these gases in the atmosphere. We haven't yet doubled. If you look at the numbers, pre-industrial carbon dioxide was about 270 parts per million. We're now just about to hit 400, so we haven't quite doubled. But we're climbing an exponential curve, so it's not going to be long before we get to that point if we don't change our consumption of fossil fuels. So within the next decade or two, we will reach the first doubling. And if we keep climbing the exponential curve, in about the same period, we'll reach the second doubling. That's the way exponentials work, right? The typical quoted number is about 2.5 degrees, maybe closer to. Some studies say 2.5 degrees. Some studies say closer to 3 degrees. So for each doubling in the atmosphere, we can expect an increase in global temperatures of about 3 degrees. 3 degrees doesn't sound like much, and this is part of the problem of communicating climate change to people. Most people, when they say, "Oh, 3 degrees," I can't even feel the difference between, if I raise the outside temperature by 3 degrees, I can't feel that. Maybe in your home, if you go from 18 to 22 degrees, you can tell the difference, kind of. But it seems small. It seems like nothing to worry about. Well, there's two things wrong with that reaction. One is the 3 degrees isn't the end of it. We're climbing up this curve. And we don't stop magically at 3 degrees, we keep climbing. The second is 3 degrees, as far as planet Earth is concerned, actually is a huge difference. So does anybody know how much colder it was in the last ice age? Okay, well, there's a problem here in that most of the school textbooks get this wrong. So if you open up any school textbook on the ice ages, or even, I think it's right on Wikipedia now, I better go and check, it's wrong in lots of other places. They say, about 10 to 12 degrees cooler in the middle of the last ice age. Well, that number turns out to be based on a misunderstanding of the science. So that number comes from the ice core records. They drill down in the ice, and as you go down layer after layer of the ice, you go further back in history. So our oldest ice core record is about 800,000 years. Right, about 800,000 years, right. And from the trapped bubbles of gas in the ice, they can calculate all sorts of things. They can calculate the composition of the atmosphere. They can calculate temperature. They've also got things like tree ring records. They've got, what else? They've got frozen leaves that tell them something about the climate. And they put all this together and they work this out. However, most of those numbers do come from the ice core data. And it's true that at the North Pole and the South Pole, it was about 10 degrees cooler in the middle of the last ice age. But the planet doesn't warm up and cool down at the same rate. In fact, what happens is the poles change at about double the rate of the average of the planet. So the equatorial zones change much, much slower. So the usual rule of thumb then is you have to divide that in half to work out what the global surface temperature average for the whole planet would have been, which basically means about 5 degrees. So 5 degrees cooler from today's climate is enough to induce an ice age where we're sitting right now, there would have been nearly 2 miles thick of ice above our heads. Okay, that's 5 degrees is enough to cause that change on the planet. What we're talking about now is we've already warmed up the planet by nearly a degree. If you look back over the last 150 years, we're close to 1 degree warmer already. We're owed almost another degree because these processes take decades to actually kick in. The planet warms much more slowly than the current composition of the atmosphere would suggest. So in other words, it takes about 30 years, if you change the composition of the atmosphere, for the planet to settle down at its new temperature. So, over about 30 years, we'll see more warming just from the changing of the atmosphere we've already done. We've also got, the time ahead of us when we're continuing to climb up the curve and burn fossil fuels at a faster and faster rate. So there's a lot of talk of 2 degrees centigrade as a safe threshold. If you look at things like the Copenhagen negotiations, all the nations of the world agreed that whatever we do, we should try and stop the Earth from rising above 2 degrees based on pre-industrial temperatures. And depending on who you ask, in the climate science community, about half the scientists that I've spoken to said that that threshold is unachievable. We've already guaranteed we'll reach 2 degrees. The question is, how much can we avoid further warming beyond that? So the political targets are viewed by most scientists as being unachievable, based on what we've already put into the atmosphere. And let me just give you a sense of some of the model experiments that do this. So here's a typical set of experiments you do with a climate model. You really want to know, as I said, we're thinking about wisdom for the future. You want to know what the future is going to look like. Well, it depends on what we do in terms of fossil fuel emissions. So the first thing you have to do is you have to work out some scenarios for likely future emissions of fossil fuels. So, for example, we might say, okay, over the rest of this century, we're going to continue to rise. We're on this kind of exponential curve right now. But let's imagine within the space of the next 20 or 30 years, we have a concerted effort to switch from fossil fuels onto renewable power. And so by mid-century, we get that growth under control. And by the end of the century, we start to reduce our reliance on fossil fuels. So that curve represents, year by year, how much more of these greenhouse gases we're putting into the atmosphere. So you work out a scenario that says, based on what we know about the technology, about the way the economy works, about how quickly we can transition to newer technologies, about how quickly we replace the infrastructure that's based on the fossil fuel economy, and we put that forward as a scenario. So it's not the truth, here's one example of how the future might look in terms of energy use. You then put that into the model and it calculates, well, what does that do to concentrations of these gases in the atmosphere? And you get some kind of uncertainty band going on here because there are uncertainties in it. You use that to calculate what's that doing to the energy balance of the Earth. So the incoming solar radiation versus the outgoing energy from the Earth, what's the difference, and therefore what's the annual increase in energy that the Earth is absorbing because of the interaction of these gases. And then you use it in this simulation model to calculate the temperature. So you get a range of temperatures, and then of course you've got 3 kinds of uncertainty embedded into this graph. One is the uncertainty about these scenarios. We don't know what we're going to do in terms of burning fossil fuels in the future. So that's one kind of uncertainty. The second is uncertainty in terms of our theories of the climate. So if you run different climate models, you get different numbers. So there's something like 25 groups around the world building these simulation models, putting different processes into their models, running them on the same experiments, and getting comparisons. So there's a spread of results here just because the different models give you different answers. And then the third source of uncertainty is the really hard one. It's what else do we not know about that we've not put into any of these models? Okay, it's the unknown unknowns. And we can't even plot what that is because we don't know. The climate scientists call it structural uncertainty. Okay, it's, well, what else is there that we didn't take account of? One of the things that isn't done very well in the models, I already said clouds, they're getting better, but they're a major source of uncertainty. The other thing is some of the feedbacks that kick in. And there are a number of feedbacks that as you warm the planet, some of these things kick in and either accelerate or decelerate the warming. So for example, if you melt the ice sheets, if you melt the sea ice in the Arctic, you replace white ice with dark ocean. Okay, white ice reflects sunlight much better than dark ocean does. So at that point, you get less sunlight reflected back into space and more absorbed by the ocean, which means you get a positive feedback effect. The more you melt the ice, the faster the warming goes. Okay, another one. If you melt the tundra across northern Canada and across northern Russia, there is a huge amount of methane locked in. It's essentially frozen peat. as it melts, as it thaws out, it releases that methane. Methane is, they call it methane in this country, don't they? I'll get this right soon. Methane. Methane is one of the most powerful greenhouse gases there is. Now, it doesn't last very long in the atmosphere. It's a very short-lived gas. It breaks down very quickly, but it breaks down into carbon dioxide. Okay, so you get an acceleration effect if you melt the tundra. What else can what other feedbacks are there? Clouds. Clouds is an interesting one. Warmer air holds more moisture. Okay, so in a warmer climate, you get more clouds. There's more energy in the atmosphere, which means you get more storms, you get more intense storms. But the clouds have an interesting effect because they're both a positive and a negative feedback. So first of all, clouds are white, so they reflect sunlight. So the more clouds there are, the more sunlight's being reflected back into space. That's a negative feedback. That tends to help cool the planet. But on the other hand, water vapor is a greenhouse gas, so it stops the outgoing radiation from the planet. So that's a positive feedback. The more clouds there are, the more we're trapping heat, because water vapor is even more abundant in the atmosphere, far more abundant in the atmosphere than carbon dioxide. So you get a warming effect from more clouds. And a lot of the discussion around this uncertainty is to do with, well, those two cloud effects. There's a positive and a negative feedback from increasing the cloud cover. Which one dominates? And the answer is, well, we've been researching this for 30 years, 40 years, and we still really don't know. The best guess at the moment is they about balance out. But it only needs a small tip in one direction or the other, and we've got a big problem. Yeah?
I have a question about, I've seen these accelerated tables before, and I'm wondering about, do they account for accelerated human response and accelerated, is Moore's law factored into these projections? I guess my question being, do they factor the fact that we can reasonably expect clean energy solutions to get better at an exponential rate?
The answer is those do not appear in these models, at least at first sight, because the only place, so there's no, in these physical models, they capture the physical climate system. There's no human activity encoded in the models at all. Yeah. Okay, so there's no feedback. So obviously there's a feedback cycle, right? As human society becomes more aware of this, the more we're going to realize we've got a problem to tackle, and the faster we'll go at it. Okay, so that's a negative feedback. Once we start to realize how bad this is, we'll get serious about fixing it. So that's not in the models. The only place it's captured is over here in these scenarios.
Well, that's probably a good idea for right? Because I I guess that's one of the things that when you get solution oriented with this, and because all of this is really terrifyingly scary, and it makes you think. Like, being presented with this data, I have a visceral reaction of, we're screwed, and there's nothing we can do.
Yep.
And I guess that's why, with this literature and with all this stuff, my question is in how much, where all this exponential stuff. Yeah. In so little of it, I what is the exponential curve for solar power?
Let me first of all show you one way in which what you're asking is captured for in some of these experiments.
Sure.
And then,
do you have any data on how the technology, how the technologies we need to improve are improving?
Yeah. So here's my answer. So right now, do people know about the IPCC and how that operates? So the IPCC is the United Nations body that assesses the climate science. And it produces reports about every 6 years. And these reports are 3,000 pages long. It's a summary of all of the science. And they're written by teams of hundreds and hundreds of scientists internationally get together, and over that 6-year cycle write. It's basically a state-of-the-art literature review. It's probably the biggest literature review I've ever seen, maybe even the biggest literature review ever conducted. And as part of that process, they get all the modelers to do a coordinated set of experiments on their models, and they feed that into the literature review as well. So the last report was published in 2007. The next one will be coming out 2014. And this is the experiment one of the experiments that's going on leading into that next assessment. They said, what we need to do is we need to agree on what scenarios we're going to put into the models. And they said, in the past, we had too many scenarios. It was crazy. We had the scenario where we go on burning fossil fuels merrily like there's no tomorrow. We had the scenario where the third world countries develop economically, relying largely on fossil fuels, but the first world transitions onto cleaner power, and then they have various mixes of those, so it depends which regions of the world are doing what. And they said, this is too complicated. Let's boil it down to 4 scenarios. And the 4 they picked are well, actually, they had to choose one of the green ones, the 4 coloured lines here. The way they do that is with a different kind of model. These are socio-economic models that capture economic development, technological development, technological change, the change of the human infrastructure, particularly our energy infrastructure. So they have a completely different kind of model. And they play with those models and they say what kinds of scenarios are realistic. And they ask the people that built those models to come up with 2 kinds of scenarios. One scenario where there essentially is no global coordinated climate policy. And that's the grey region here. So if you run all of those different models, and they've all got different parts of the socio-economic activity captured in them, you get a spread. This is over the coming century, or the rest of this century, I should say. You get a spread that looks like that in terms of emissions this is gigatons of carbon dioxide. So you get a spread like that by the end of the century. And so they said, what we'll do is we'll pick a high and a low scenario to kind of bracket them. So they picked this one up here, which is kind of the most pessimistic of these models in terms of emissions growth. And AIM is reasonably optimistic to capture this spread. And then they said, right, we also need scenarios to capture what we can do with coordinated global climate policies. So they got the modelers again to do runs with various different assumptions in about climate policy, and that's what the blue region represents. So the blue region represents kind of best and worst case brackets. Actually, the coloured regions here are a 95% confidence interval. So the 95% confidence interval for all these different models will look like that for coordinated climate policy. And then they picked a high one, the red line, and a low one. Then, having discussed that, notice this top green line here goes exactly along the bottom of the blue region. In other words, that's the 5% level. So below that is vanishingly unrealistic. And the climate scientists looked at that and said, that's not going to be enough to keep us within that 2-degree threshold. They said we want an even more ambitious scenario than that put in. So they went back to the modelers and they came up with one that comes down here. What's interesting about this scenario is, here's the 0 point on the graph. So in about, 2070, that crosses the 0 point. So in other words, we reach 0 carbon emissions by 2070, and then we go negative. How do we go negative? Every year that means we have to be taking out more greenhouse gases from the atmosphere than we're putting into them. Well, it's possible. Okay, planting huge numbers of forests, coming up with some crazy technology that just sucks this gas out of the atmosphere. And there are prototypes. Nobody's demonstrating how to do this cost effectively, but there are machines that will do it for a huge energy input. Well, where are we going to get the energy to drive these machines? But anyway, so imagine some future in which by 2070 we go carbon negative and start removing it from the atmosphere. That's the lower scenario. So then you put those 4 scenarios into the climate models and you get, climate models, and they use those to calculate what will the concentration of these gases in the atmosphere look like. And then you do the temperature experiment using your physical climate model. So you've got different models that you're wheeling in and out for doing this. So this is, by the way, I should warn you, this is the result from one set of runs from one model. So this is folks out in Colorado. Right now, the scientists have got all the runs and they're trying to put them all together and draw the graphs to show what the spreads are. So beware, I've got no confidence intervals on here because it was one model. But here are the 4 scenarios. They didn't continue the lower of the no policy scenarios beyond the year 2100, but the rest they continued for 3 centuries. Remember, this is a lot of computational power to compute these, which is why they chose to stop one early. So the worst case scenario on this graph takes us up to, here's you have to be careful where the zero line is as well, because on all of these graphs, they tend to make zero the average global temperature for the last quarter of the 20th century. Well, that's not pre-industrial temperatures. That's already quite a bit warmed up from pre-industrial. So pre-industrial is down here at about -1. Okay, so all of these scenarios cross the 2-degree threshold by about 2040. Although the green one doesn't quite cross it. What happens is it takes us up to about 2 degrees and stays there with, you start to see a slight cooling by the year 2200, significant cooling starting to happen by 2300. But notice this is where we are now. Throughout the rest of the next 3 centuries, even on that most optimistic scenario, we're warmer than the climate of today. And that's with these crazy carbon dioxide capturing machines, whatever they're going to be. The blue line is the more pessimistic of the climate policy scenarios. So somewhere between those two is probably realistically what we can achieve with coordinated policies. And that basically means emissions reduction targets, a price on carbon, and a coordinated effort to stop building coal and oil energy infrastructure and to start building renewable infrastructure. And then if we forget about climate policy, this is the worst case scenario. This is if we don't do anything about climate change and we keep on burning fossil fuels as our primary resource, and the rest of the world develops to the kind of lifestyle that in the West we lead. That takes us up to, actually it's about 9 degrees warmer, because remember I've got to add 1 because my 0 point really is here. So about 9 degrees warmer by the end of 3 centuries. Okay, so when we say, and I take your point, this is very depressing and what the hell do we do about it? Well, this is what we can do about it. We can avoid that future and we can have a future that's somewhere down here. Okay, that's why action on climate change matters. And it's not this is a problem that we can't solve, we just should give up. This is a problem that we've still got everything to play for. Okay, because we want to avoid that future and we want to pick a future that's down here, preferably on the lower end of this. At the same time all that's going on, the planet is warming. I mean, this takes us to about 3 degrees warmer than pre-industrial levels. In the worst case, just up to 2 degrees and then a slight cooling in the best case. Okay, that also has a massive impact on human activity. There is a lot of infrastructure will not survive that. We'll see increasing storms, increasing floods, increasing high-intensity hurricanes. We'll see increasing heat waves across certainly equatorial zones and maybe some of the more temperate zones. So at the same time as we're switching off fossil fuels and switching to renewable power, we've also got to build the adaptation to allow our infrastructure to survive that warmer planet. But at least we're not up here. You know, this is where we should be heading. I don't know if that's a more optimistic message than the despairing one. But it does suggest to me something very important, which is there is a hell of a lot to fight for. There's a lot of difference to fight for.
I agree. It's like 2300. Like that's such a.
Right. So who thinks that far into the future, right?
Well, like we could be on Mars. Like it might, like you know, like I get, like, I mean, it's just so. At that point, like I find it difficult to fathom what the world would be like in 30 years, right? Because if you ask anyone in 1980 what 2012 was going to be like, every single one of them is wrong, except maybe Ray Kurzweil. But
so this is where those uncertainty factors I talk about kicked in. Because again, there is a huge, we just don't know. But this captures the best that we do know. And so you say, okay, well, something might come along and save us. Are we going to wait for that, or are we going
no. Like obviously not. It's just like
someone might invent a new technology tomorrow that fixes this problem overnight, and that's entirely possible. I
the only way they'll do it is if they see this first.
Right, which then brings me back to the challenge that I was talking about. Some of my research is geared to, which is how do we get people to understand this? You know, well, you make them sit and watch an Al Gore movie. Fine, they sit and watch the Al Gore movie, they munch their popcorn, and they go back to their lives. And one of the things, has anybody seen the DVD of The Inconvenient Truth? One of the things that really irritates me about that DVD is you watch the movie, and he does a reasonable job of getting across the science. There's some bits where he slightly exaggerates, there's some other bits that he's missed out, but overall, it's a pretty good factual presentation of science. You get to the end of the movie, and then it says, what can you do? And then it starts talking about changing your light bulbs. Okay. This is not a problem that changing the light bulb solves. Okay, this is a problem of completely reinventing human infrastructure across every sector of industry to make sure that we no longer need fossil fuels for transport, for heating, for shipping goods, for manufacturing, for cement production. Cement production produces a huge amount of carbon dioxide. Okay, so this is a place where we stop thinking about the guilt of, oh, I didn't turn my thermostat down or I didn't change my light bulbs. Those things are irrelevant. What is relevant is getting together with communities and thinking about how do we do this via collective action. Part of it is political, of course. It's putting the pressure on the politicians to actually do something. But part of it is also not changing the politics, but changing the way we think about the problem and the way we start talking to each other about the problem. And maybe those two are highly connected. The political and the social spheres intersect in complex ways.
Like, I guess to respond to that as well, like if it is an infrastructure problem, then isn't the only solution a technological one? Like, isn't there a certain measure with which the green lines are predicated on, their success is predicated on a technological, on almost a technological revolution?
To some extent, yes. To some extent, this is a problem of getting out new clean technology as fast as possible and replacing the old technology. Now, if you phrase it as this is an invention problem, we have to invent that technology, no, it's not. There are a number of analyses of clean energy that say, actually, we could replace the vast majority of fossil fuel needs with clean energy today using current technology. So the barrier isn't an invention one, it's an adoption one. How quickly can we get the world to adopt technologies that already exist? They're typically not yet cost effective because they have not been...
the economy of scale.
You haven't reached an economy of scale. There's been a massive growth in solar panels over the last 3 or 4 years. In fact, we're on this beautiful exponential curve for installation of solar panels. And with that, it's driven the price down to the point within the next couple of years, solar energy will be competitive price-wise with fossil fuel energy production. And then, of course, there's this question about what kinds of subsidies are there for each, and how do the subsidies mess up the relative pricing? Because there's massive subsidies for fossil fuel extraction. There are subsidies at the moment for the clean energy industry. Well, what's the distorting effect of those two subsidies, and should politicians be rejigging it? One of the things that I'm interested in, and I don't know how to put figures on this, is imagine the whole system, and here's my best attempt to do it. We've got up here in green the kind of physical climate system, so we've got this process whereby emissions from the burning of fossil fuels change the concentrations of the atmosphere, change the climatology of the planet. That has an impact in a number of different spheres, calculate what those impacts are, and then, how does that get portrayed in the media? How does that shape public opinion, and then how does those things plus direct knowledge of this start to reshape policy decisions at any level of government, whatever level you look at? And then how do those policy changes rejig the economy to change the way that we use energy? And then, of course, there's my original diagram didn't have feedback effect here where there are lobbyists who look at different parts of the economy, different industrial sectors, for example, and go and whisper in the ear of the politicians and say, oh, our industry is losing out, you've got to do this. So, and that often works in the opposite direction because that becomes a positive feedback, that as soon as politicians start to talk about things like a carbon tax, the industries that are most impacted, that pay those politicians campaign funds, whisper in their ear, say, don't do a carbon tax, it'll kill our industry. And by the way, here's a few more thousand for your re-election campaign. So there's that process going on there as well. So the idea was, we'll think about this whole system and think about where changes need to be made to fix this entire system. And largely, oh, and the other thing I wanted to do was figure out delays. So there's a certain amount of time it takes to get different things done. And I told you about some of the delays across the top of this system here. So I said, you know, for any change in, let's say, change in the concentrations of these gases in the atmosphere, it takes a few decades for that to really, for all the impacts on the climatology to play out. Okay, so I know there's a delay of the order of 30 years from here to here. Okay, well that delay is unfortunate because that means we don't see the impacts early enough for the media and public opinion to be shaped by them. There appears to be an interesting effect going on right now in public opinion because of the heat waves across North America this summer. So it's the hottest summer in recorded history. That plays into the way the story is portrayed in the media. So how quickly does recognition of the impacts feed into the discourse that's going on here? Well, it still takes some time. And then how quickly does, if public opinion changes and the way these things are portrayed in the media, how quickly does that shift government policy? In some countries, it will require a change in government before you will get any change in policy. And I certainly think that's true of Canada right now. Whether it's true of the States or not, I don't know. So, you know, you have to wait for the election cycle to play out. So there's another delay. This link here is very slow. So policies that are geared towards a switch from fossil fuels to clean energies will take decades to have any significant impact in emissions. Because, you know, there's a limit to how many new wind turbines and solar panels we can install each year. And all the time that we're installing those, energy demand is still going up and up and up. So one of the things that's happening right now is we're building wind turbines and solar panels faster than we ever have before. We're climbing up this exponential. But at the same time, we're still building more coal-fired power stations and building more oil refineries because the energy demand is still growing faster than our ability to install clean energy. So we've got this effect going on where, sure, we're building this stuff really fast, but we still can't keep up with demand. And the missing demand will be taken up with fossil fuels because that's readily available. So how long does it take for significant policies here to really turn the economy around so that we can get over the crest of that curve? At what point will emissions peak and start to come down again? And that's probably of the order of decades. So if I add up all the delays in this loop, the question is, well, how do I accelerate it? And I think a big part of the answer has to be accelerating this part of the loop. You know, getting the message out for, well, what's happening right now? How's that going to change over the next few decades? What are the impacts going to look like? And changing public opinion. And it's not, and this is another problem with how this is portrayed in the media. It's typically portrayed as, well, this summer caused all these droughts. That's a problem. We should start doing something about it. And that's not the right story, because the right story is we're on this trajectory. It's an upwards trajectory. If you thought this summer was hot, where are we going to be in 10 years, 20 years? And you never hear that reported in the media. The media just reports, oh, there was these heat waves, and they're probably related to climate change, and we should do something about it. And I never saw one single media story this summer that said, this is part of an ongoing change process rather than a destination. So the media says, this is our destination. Oh, we get these heat waves. It's going to be more like this summer. Yep.
What are your thoughts on, I'm trying to formulate my question, sorry. I know, I'm from the US, and I know that the U.S. military has been sort of very quietly, because it's not politically savvy to do anything having to do with climate change in the U.S., doing tons of research and technology development to combat climate change, because it puts their troops at risk all over the world.
Yep.
And so I see that the military is not in there, and neither is sort of the technological innovation that has been driven by the military in the last century and will be. So, and that's something that is totally outside public opinion and all that sort of stuff. That's just a bunch of people who have a lot of money saying this is a problem that is affecting us. And so how do you think that that's going to, I guess, how do you think that is going to translate out into the broader society?
I don't know, but the best source I know on this is Gwyn Dyer's work. You haven't seen it. There's a fabulous book called Climate Wars, and and there's a series of podcasts as well from the CBC. So Gwyn went and interviewed people high up military planners in a number of different countries, particularly in the US, over the space of several years, and said, what are you doing about climate change? And what emerged is exactly this. We're doing a lot about it. We're taking it extremely seriously. Now, what he focused on in the book and in the podcasts is much more the question of strategic planning for a climate changed world, rather than the technological change that the military are putting in place. And they are putting stuff in place to reduce their impact on fossil fuel energy. They're worried about things like battlefield supply lines. We have to ship all this oil across battlefields to supply energy for the troops, and that's a huge vulnerability. Wouldn't it be better if they had their own energy generation capacities with them? So, there's all sorts of strategic reasons to do that. But the book focuses on what are the geopolitical implications of climate change, and the military planners are gaming this, the way they do strategic planning over the next 10 or 20 years. What army do we need? What war will we be fighting next? Is the question they ask themselves. And they say, well, as the climate warms up, the following kinds of things can be expected. And there's several really thought-provoking scenarios in the book. One is the massive migration across the Mexican-US border. Okay, because as the planet warms up, large parts of Central America become really hard to survive in. And so, we get this massive migration of people across that border. That border is already a disaster zone. Okay, we already have huge weaponized systems across large stretches of that border. So he says, what's going to happen when people start swarming it? Because they have to migrate because there's no food and there's no water south of the border. There's another one that he sketches out, which is the likely war between India and Pakistan over water supplies. So both countries are largely fed by essentially 4 rivers coming off the Himalayas. As the ice melts, those rivers dry up. There is not going to be enough water to adequately supply both countries for their agricultural and human consumption. What happens? Well, here's 2 countries that historically don't get along. Okay, now they start fighting over water supplies. Both of them have nuclear weapons. Okay, what happens then? So these are the kind of scenarios he sets out in the book. But it doesn't really answer your other question, which is there a good news story here in the sense that the military is ahead of the rest of us in getting this technology rolled out, and maybe that will transition into civilian technology? I don't know. That's an interesting question.
Maybe we could just give all their money to the scientists.
Be nice.
That would probably fix things pretty fast.
Yeah.
What are your thoughts on eco-cities? And considering that roughly 80% of the world's energy supply is going towards cities, and there's this kind of redemption process that's happening now in order to counter what cities and deriving all of their energy from fossil fuels have been creating this argument that eco-cities are a solution to this. Do you have any thoughts on that?
Yeah, absolutely. I mean, thinking about this over the last couple of years and thinking about, where are the most likely solutions, I haven't thought about the military, so that's an interesting one to start thinking about. But I actually think cities are the biggest part of the answer. So cities reinventing themselves as low-impact cities. Now, not coincidentally, we ran a workshop last week with a whole bunch of people that think about cities and how cities work and what a sustainable city looks like. And some really interesting ideas emerged from that. But the kick-off keynote speaker was a guy from Toronto who studies sustainable cities, Jeb Brugman, who has a book out called, what's his book called? Oh, you can Google it. His name is Brugman with 2 N's at the end. And his argument is that there's a lot of talk about cities, or at the moment largely it's confined to districts within cities, kind of the zero carbon district. And there's a number of these in Europe and a few growing up in Australia, where they've built an entire new subdivision of zero energy houses. And there's technology to do this today, and they work, and they're price competitive with traditional building technologies. And so he says, well, this is great, but if cities really going to play the bigger role that they ought to play in global climate change, we have to think of cities not as net zero emissions, we have to think about them as net positive, by which he means overall the city is actually playing, the part where my green line went below the zero, they're playing that role. And so he has this vision, and he sets it out in a number of different regions, how a city can be reinvented instead of being this massive engine that pulls in resources from the surrounding regions, food, energy, minerals, whatever, and produces wastes that somehow have to be disposed of. He says, no, think of the city as it's a net productive thing. It actually generates its own resources. It generates more energy within the city than it consumes. It recycles its water, so it produces more clean, usable water than it consumes. It mines its own waste, and he talks about mining your landfills to reclaim minerals, metals, especially precious metals. We've got to the point where mining landfills to reclaim some of that waste material is actually now cheaper than building a new mine, digging it up from untapped resources. He says, imagine a city that reprocesses all of its own waste, that takes the rain that's falling on that city, turns that into productive clean water and produces water for the surrounding region rather than the opposite. With solar power and wind power and growing some of its own food in these vertical farms, producing more food than it consumes. He says, if you crunch the numbers, it's possible. Yeah.
So I guess to sort of address your big question for the presentation, which is like, how do you turn this into wisdom? So what do you think when you're in a city like Toronto, where the rhetoric is about the war on the car, and they want to build a diesel train that connects downtown to the airport? So how can, in terms of community action, when they frame the debate so it's subways versus light rail, and that's what they have people fighting about, which is totally.
This is really hard.
Yeah.
So one of the speakers we had at the workshop last week, which I was delighted about, we had David Miller, our ex-mayor, came in and gave us a talk. And we asked him for his talk to say, what would you like to have had? We were talking a lot about evidence-based policymaking. So we said to him, what would you like to have had in your time as mayor to improve your ability to make decisions, to make the right decisions for the city? And by the way, having now met him and chatted to him and seen his talk, I'm in love with David Miller. He was a fabulous mayor, and he really drove this city forward in terms of sustainability issues. And he said, you know what? He said it was never lack of evidence that was the problem. He said the problem was our ability to tell the appropriate story to get the community on board. So he talked about a number of decisions that were made in his time as mayor, which, had they survived, would have been very good. But in each case, they were largely overwhelmed by their inability to make the case about why this was something we needed to do. And he talked about Transit City, and that passed through Toronto City Council. I don't remember the exact numbers, but it was something like 44 votes to 1. And you know who the 1 vote was? Our current mayor. And so Transit City just sailed through council, they got the province on board, the whole thing was going to be built with all these light rail. And then, of course, a couple of other interesting things happened. One was, and really only hearing him tell me this last week did I start to understand the impact of this. One of the things that they waved through, again, with almost no opposition on council, was the removal of the fifth lane on Spadina and the putting those bike lanes in. Okay. This passed through council, it just sailed through. Again, there were 1 or 2 votes against, and you can guess who they were. All the environmental impact assessments were done, all of the community consultation was done, and there was universal belief that I don't know if you remember what it was like. It was this flow lane. So in the rush hour in the evening, the middle lane was flowing south, and everybody agreed it had to go. And the only question was, if you remove the fifth lane, what do you put in place? Do you widen the sidewalks, or do you build bike lanes? And that was what the community consultation was about, and there was a lot of disagreement about exactly what it was, but there was universal agreement that fifth lane had to go. And the numbers show that it reduces your throughput by about 2%. So car journey time on Spadina was about 2% slower once they removed this fifth lane. And that's what the data has shown since they removed it. This all passed through council, they got going, and then the next day after this decision was taken in Toronto City Council, the National Post, on its front page, published that headline, Toronto's War on the Car. And he said nobody saw that coming. Not him, not his civil servants, not any of the people associated with these transit plans saw that one coming. And so suddenly now, just because we're taking out a car lane and putting in some bike lanes, suddenly now there's this war on the car. And then if you think about how history played out after that, that's what got Rob Ford elected. It was a large number of people who rely on their cars, suddenly had this idea in their heads that David Miller and City Council were conducting a war on the car and it had to be stopped. And it's because we were putting in 2 bike lanes on Spadina. And by the way, that's why City Council voted a couple of weeks ago to remove the bike lanes. They have to go because that's symbolic of this war on the car, not for any other reason. Okay, they're a symbol in this battle. Well, I don't know, does that story help you answer your question?
I mean, I think it's interesting that it is a systemic problem because North America was built for the car. Right. Suburbs were built because people use cars. So as soon as you start, so it's not as easy as saying I'm a cyclist and whatever, and I live downtown, so that's easy for me. But if I didn't live downtown, suddenly that's not easy for me. Right. If suddenly the gas prices start rising, and in downtown there's some kind of toll to get into downtown, suddenly that creates a lot of barriers for people who it's not their fault that in the 50s the infrastructure was built for the car. Exactly. And so how do you start to, how do you even start to deal with that when the infrastructure is in place and people cannot get from their home to their job?
Yeah. Well, the solution then is to target the car. But no.
Ramp up the war on the car.
The infrastructure, no. Or you change the car.
Well, yeah.
You radically reinvent what it means to own a car.
And they're trying.
And to give my wild speculation, it means electric-powered self-driving cars, right? And the technology's here, right? And so as long as we can push that through, that's one in I think the thing here is we have to choose our battles very, 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 very carefully, and you have to find out what the target element in the infrastructure is, recognize what the public opinion is. People love their cars and they're not going to give them up. So then you have to change their cars first, and then you can fight the battle for the bike. Then you can start to weave them out, right? And from my perspective, you saw an electric-powered self-driving car solves the double problem of massive carbon emission and public transit, because gradually you can face it, and also roadside accidents. It solves so many human problems. To me, it's staggering that we aren't putting every cent of our money into it. Not to pontificate, but.
So going back to this chart, which I think is really interesting, I actually looked at a little bit in another class at public opinion and on climate change specifically, what affects that. And a couple of studies that I read that I don't have at my fingertips, they looked at it and they decided that one of the primary drivers of public opinion in the United States specifically was something called a lead signal, and that is, what do politicians say, what do the political parties say about that. So it's as if there's more feedback loops going from policy
Right.
or government back to public opinion and back to the media,
Yeah.
which I think makes it even more complicated and hard to determine where the lever point is. And you actually change the bottom part of that graph, which then goes beyond emissions.
Right. Yeah, I think that's true. And I don't understand American politics at all.
There's a really interesting graphs that I saw where they look at education level, and if you're liberal or conservative, and liberal, you're more educated, more likely to give the correct answer concerning climate change. Conservative goes in the opposite direction.
Yeah, there was a study done at Yale.
I think that goes beyond just climate change.
They put that evolution too, I think.
Yeah, it feeds into a theory of social epistemology, which is that increasingly people filter the facts based on their prior beliefs. So instead of listening to all the facts and kind of making up their minds based on them, they do it backwards. They have the prior beliefs, which are largely ideological, and they choose not to listen to things that are inconsistent with those facts. So what they hear is just the things that bolsters those beliefs, which is why you get that effect. You know, on the right wing, there's a certain ideology that talks about certain things, and certainly when it comes to climate change and a number of other things, it objects to the whole idea. So it filters out facts and refuses to talk about them. And some writers say, yeah, there's equally things going on the left wing.
Sure.
Yeah. Facts are filtered out.
Just as an observation, I think one of the funny things is that a lot of people, for possible solutions, seem to come up with progress-driven ideas, and I think that this is really having our blinders on, thinking that technology is going to save us. But that's just a whole other aside. But my original sort of question I was going to ask you, I saw this in the Australian media actually, so maybe you would know more about it. But apparently, a few summers ago, or last summer, they were installing so many solar panels in Australia that they actually had to put a temporary ban on installing solar panels because it was putting so much energy into the system. But no one, I read a whole bunch of articles on it, and not a single one of them mentioned, well, why don't we just cut out one coal power plant from the system?
Okay, so there's a simple reason for that, and it's to do with the differences in demand over a 24-hour cycle.
Oh, because they don't have a battery.
Yeah, exactly.
Yeah.
So what you have to do is the solar power, gets you energy during the day. It doesn't get you it at night. And if that doesn't match the ups and downs of peak demand, coal-fired power stations are your backup. If demand suddenly goes up, you turn on another coal-fired power station. You always have a number kind of on hot backup that you can just switch on to meet demands, and when demand drops, you switch it off again. You can't do that with solar. So
I guess there's the assumption that we're going to progress and make a battery, but if we never do, then solar.
Well, exactly. So you have to then install the storage capacity for all the extra electricity that you're generating you can't use immediately, and that takes time. So it sounds like what happened was they got ahead with the installation of the panels and fell behind on the storage capacity. They're generating electricity you can't actually use because it exceeds the demand at certain times of the day.
So something like wave power would probably, or something that's constant.
Wave power is more steady, yep.
Wind even cuts out.
Wind has some of the same problems as solar, although if you have distributed wind farms over different parts of the country, there tends to be very little correlation between windiness in different parts, especially countries big as Australia or Canada. There's very little correlation. So if you can ship the energy across the country, wind is a lot less bursty like that than solar power is. But you also need the storage capacity if you're going to use it for things like transport, where you've got to carry the capacity around with you. So the storage capacity is one of the, if you are looking for technological things, electricity storage is one of the biggest challenges where we do need some better technology.